Okay, so what is the advantage of using Bode plot? Bode plot, as I said, is an approximate plot. It's not an accurate plot. It's an approximate plot, but very close to the real plots. Now, since we are dealing in the logarithmic scale, the biggest benefit of using Bode plot is anytime you have a transfer function, all the products become additions. Remember, in logarithmic scale, any product is represented by the log of each number that is being multiplied together, the log of each number added together, right? And any division becomes subtraction. So instead of multiplication and division, you can write in decimal scale and logarithmic scale your transfer function in terms of additions and subtraction. And if you plot each individual factor of the transfer function, then you can add or subtract those each individual function on the plot to get the complete Bode plot. That's the biggest advantage of Bode plot, right? So what different types of factor can you see in a Bode plot? Now there's one thing that I'm not going to be discussing. I don't think we have enough time to discuss that. It's a little complicated, not extremely complicated, but I don't think it's useful here. I don't think I'm going to be asking in the exam, which is basically Bode plot corresponding to a quadratic equation, right? So we're not going to be discussing quadratic equation over here. Now, if you have a constant value, a gain, constant gain, and you take the log of that, 20 log of k, that's just going to be a straight line, right? So you're going to create a straight line anytime you see a constant value. You take the log of that, multiply that by 20, and that's going to be a straight line. Anytime you have a pole as j omega or 0 as j omega. Remember, poles will be in the denominator of the transfer function, zeros will be in the numerator of the transfer function, right? So anytime you have that, let's say you have a function 100 over j omega, right? So if you take 20 log of this, 20 log of the magnitude of this, sorry, then the magnitude of this is going to be 100 over omega, right? This right here, magnitude of this is 100 over omega. So when you take the transfer it into decibels, 20 log of 100 over omega is going to be 20 log of 100 minus 20 log of omega. So you have 20 log of 100, which is 40. So you draw a line here, which is 40, right? This will be the 40 line. And then you're going to do negative 20 log of omega. Here the cutoff frequency is what? 1. In the denominator, you don't have anything, that means it's 1, right? So anytime your frequency is less than 1, you will assume it to be 0. Anytime it is greater than 1, you are going to be assuming it to be what? You're going to assume it, well, there is no 1 plus there, but anytime it is greater than 1, then you're going to assume it then it is decreasing with respect to negative 20 decibel per decade. So basically what we see over here, at 20 log of 1, this value will be 0, right? This value will be 0, this is 1 right here. This line is not y-axis, but this line is 1. So the value will be 0 for 1. And as we move away from 1, every 10-fold of frequency, so the first 10-fold is going to be 10, from 1 to 10, right? At omega is equal to 10, it's going to become 20 log of 10, which is negative 20. Log of 10 is 1. So at, I'm just drawing right now this one, right? So I will have, it starts with 0. At 10, it is going to be negative 20 decibel. At 20, it's going to be negative 40 decibel. Look at my mouse. At, not 40, sorry, at 100. At 1000, it's going to be negative 60 decibel. Okay, so now you have two functions. You have a graph corresponding to 20 log of 100, which is 40 decibel line. And you have a graph corresponding to negative 20 log of 100, which starts at 1 which is before 1. Let's say you're starting with 0.1, that is okay, it's going to be 0 at 0.1, but at 1 it is going to be 0, and then it's going to start dropping with a slope of negative 20 decibel per decade. So what you're going to do, you're going to add both these lines together. You're going to add the 40 decibel line, and you're going to add this line, which is, I'm not showing here. Let me see if I can draw that line. Let me grab a line. So it's going to be this line right here. Right? Okay. And let me go ahead and perhaps, let's see if I can change the color to some, oops. And so change the color to some lighter color perhaps. Okay. Where is it? Drawing tool, and let's say line color. Let me make it light. Let's see. Okay, let me make it even lighter. Okay, I think that is fine, right? So this line is corresponding to this function, negative 20 log of omega. It has the slope of what? Let me put it. It has a slope of negative 20 decibel per decade. Oops, fonts are simple. So let me go and change the Times Roman and make it smaller perhaps. 8 size is okay. Okay. Alright, so this line is corresponding to this. Now what's happening? You're gonna add these two lines, the 40 decibel line, which is corresponding to this right here, and this line, negative 20 decibel per decade. So at frequency 1 radian per second, you have 40 plus 0, right? So the value is 40. At the frequency 10 radian per second, you have negative 20 and you have positive 40, right? So the value is going to be positive 20. At 100, you have negative 40, you have positive 40, value will be 0. At 1000, you have negative 60 and positive 40. The value is going to be negative 20. So this will be the Bode plot right here. When you add both these lines, this will be the Bode plot right here. Right? It is going to be going down with a slope of negative 20 decibel per decade. It's going to pass through 100 radian per second when your value is 0 or x-axis. Right? So that's going to be the Bode plot corresponding to this. Now, if you have a 0 instead of a pole with omega, let's say you have 100 omega, assume 100 omega instead of 100 over j omega, you say j 100 omega, right? If you have j 100 omega, then what's gonna happen? J 100 omega, let's say, right? So when you take the decibel scale, magnitude of j omega in decibel will be equal to what? Magnitude will be 100 omega. So that's going to be 20 log to the base 10 100 omega, which will be equal to, let's do it here, equals 20 log of 10 or 100, sorry, not 10, 100, 20 log of 100 plus 20 log of omega, right? All right, so I'm just going to put down, since I'm adding this in the notes, I'm just going to put down this as example of 0 instead of pole, example of 0. So now what's going to happen? 20 log of 100, right? Same thing as this, 40 decibel. So you will have a line at 40 decibel. 20 log of omega, right? When omega is 1, value will be 0. When omega is 10, what will be the value? 20 log of 10, log of 10 is 1, value will be 20. When omega is 100, value is going to be 40. 1060. So you will have a line. You will have a line of 40 decibel, which is corresponding to 20 log 100, and then you have a line. Grab line again. I already have it, I guess. You have a line which is going like this. How it is going? 20 decibel per decade, not negative 20, 20 decibel per decade, right? So you have a 40 decibel line, and the other line is going, it should be going from here, hold on, it's going from here, starting at 0, right? Starting at 0. So when you're gonna add these two lines, what you're gonna get? At omega 1, you have 0 and you have 40, so it's gonna start at 40. At omega 10, you have 40, and then for this omega 10 is gonna give you what? 20. So you're gonna have a 60. So at 10 it's gonna go up 60, and then 80, and then 100, and keep on going. So the slope of the line is going to be 20 decibel per decade instead of negative 20 decibel per decade. Okay, 20 decibel per decade. So when you have a 0, it's going to correspond to 20 decibel per decade increase. Okay, let's look at, you have multiple poles or multiple zeros, j omega cube, j omega square, whatever. Now remember, multiple poles mean what? You can break it down in terms of omega times omega times omega, or omega times omega, right? Now anytime you have, for example, you have this transfer function, you take the decibel, 20 log of 1000 minus 20 log of omega cube. Now remember, when you have 20 log of omega cube, when you have a power, it will come here and multiply this factor. So it's going to become 3 times 20 log of omega, 60 log of omega, right? And then 20 log of 1000 is 60. So it's going to be 60 minus 60 log of omega. That means this thing is going to go down with what slope? This was going down by 20 decibel per decade. This is going to go down by 60 decibel per decade. So each decade of frequency is going to go down 60 decibel. And then this will be constant 60 decibel. So when you draw both of these lines and you're going to add them together, you're going to see that the line, it is going to be at 10, it is going to be at 1, it's going to be 60 decibel. At 10, it's going to be 0. At 100, it is going to be negative 60 decibel, so on and so forth. Okay. Alright, fourth case, poles or zeros at j omega is equal to omega 1. Remember the first order RC circuit that we discussed? When you have the cutoff frequency omega 1, that's the same case. So let's look at an example. 66 j omega plus 1000 divided by j omega over 100. The first thing you're going to do is you're going to write this in terms of 1 plus j omega, right? So you're going to divide the numerator by 1000. You're going to divide the denominator by 100. So this is going to become 66 divided by 1000, 1 plus j omega over 1000. And the denominator is going to be 1 over 100, 1 plus j omega over 100, right? And then 1000 and 100 is going to be 10. So it's going to come out to be 660, 1 plus j omega over 1000 divided by 1 plus j omega over 100. So now you have 3 factors. You have a 660, you have this 0, you have this pole. You're going to convert this into decibel. First you're going to take the magnitude, then you're going to convert this into decibel, and then all the products are going to become addition, and the division is going to become subtraction. And then you're going to plot each one of them separately, as we discussed earlier, and you're going to combine all the plots to get the final Bode plot. Okay, explanation is given here. Read that, and it's going to look something like this. In the light gray lines, I'm plotting the individual plots. Right? This is the constant value, 56 decibel, which will correspond to 20 log of 660. Let's see, the one that is going up is corresponding to the 0, right? At omega is equal to 1000, it is going to be 0 up to omega equals 1000, and then after 1000 it's going to start going up by 20 decibel per decade, and this is going to be 0 until omega is equal to 100, and then it's going to start going down by negative 20 decibel per decade. So this is the pole right here. So you're going to take and you're going to add all these 3 gray lines, and the result will be something like this, what you see in the red line. Okay, so do it, don't just read it, do it. And the fifth and last case is if you have multiple poles or zeros. That case is similar to what we have over here, right here. If you have j omega cube or square and stuff. So an example is given here: 56 exponent 6, s plus 20,000, s plus 12,000, s plus 6,000. The problem that will be given to you will be in terms of s. Remember, s is j omega, right? So you're gonna replace s by j omega. So first we're gonna do divide the numerator by 20,000. First, actually, we replace s by j omega and then divide the numerator by 20,000. We're gonna get 1 plus j omega over 20,000, and then divide the denominator by 12,000 for this one and by 6,000 for this one. So 1 over 12,000 times 1 over 6,000, right? So you're going to get, or we can take 12,000 as a common factor out, so it's going to be divided by 12,000. So 1 plus j omega over 12 exponent 3, 1 plus j omega over 6 exponent 3. So we take 6,000 as a common factor out, we take 12,000 as a common factor out, right? So this we're gonna get a constant value that we're gonna simplify. Is gonna come out to be 2.59, and then we have 1 plus j omega over 20 exponent 3 divided by 1 plus j omega over 12 exponent 3 times 1 plus j omega over 6 exponent 3, and this is a square. Actually, I forgot to say this is a square. So that's why it is 6 exponent 3 is square that I took out. You can split this into 2 factors. Remember, 1 plus j omega over 6 exponent 3 times 1 plus j omega over 6 exponent 3. Same thing, like I'm showing you over here, right here. Okay, so now you're gonna plot the Bode plot corresponding to each one of them. So 20 log of 2.59, which is 8.27. So a straight line for this. 20 log of this factor, the magnitude of this factor. So as long as it is less than 20 exponent 3, it is 0. When it will start going beyond 20 exponent 3, it's gonna start getting a slope of 20 decibel per decade. So let's see where it is, right here. Up to 20 exponent 3 is 0, and then a slope of 20 decibel per decade. Alright, poles. This will be 0 until 12 exponent 3, 12,000, and then it's gonna go down by negative 20 exponent 3. So up to 12,000, 0, and then it's gonna start going down negative 20 decibel per decade. And now the square one, remember, when you take 20 log of this, what you're gonna get? Negative, let me do it here. You're gonna get 20 log of what? Square root of, and the value is squared, so square root of 1 plus omega over 6 exponent 3, and let's see, so that's going to be one term, omega over 6 exponent 3 square, square, let me put omega here as well, So that's one term, right? And then the second term is going to be the same, Control C. So that's going to be minus actually. Remember, it's the denominator, so minus. And then the second term is going to be same. Oops. Minus. And then I'm just going to copy this. Control C. Okay. So you have these two terms, right? They're going to be in the numerator with a negative sign because they're dividing, and the magnitude of each is going to be negative 20 log of square root of 1 plus omega over 6 exponent 3 square. So both of these, when you add them together, it's going to be negative 40 log of square root of 1 plus omega over 6 exponent 3 square. So as long as it is less than 6 omega 3, you have 0. When it is greater than 6 omega 3, you're going to have negative 40 log of omega over 6 exponent 3. So every decade of frequency, 6 omega 3 or 6 exponent 3, sorry, 6,000 to 60,000 is going to drop by negative 40 decibel, right? Negative 40 decibel. From 6,000 to 60,000 is going to drop by another negative 40 decibel, right? So you're going to have negative 40 decibel, negative 80 decibel, negative 120 decibel. So this is the line right here. Negative 40 decibel per decade from here. And what you're going to do, you're going to add all the lines together, and you're going to have something like this: 8.27 until 6 exponent 3. Then it's going to start going down with the slope of negative 40 decibel per decade until it will hit the 12 exponent 3, which is this. When it will hit 12 exponent 3, then it's going to start going down with the slope of negative 60 decibel per decade, because remember, 12 exponent 3 is going down by negative 20 decibel per decade after 12 exponent 3, 12,000. So if you add the slope of both the lines together, it's going to become negative 60 decibel per decade. It's going to go negative 60 decibel per decade until it will hit 20 exponent 3, 20,000, 0, this one. And then this line is increasing with 20 decibel per decade. So now negative 60 decibel per decade plus 20 decibel per decade is going to become negative 40 decibel per decade. So negative 40 decibel per decade. And that's going to be the final Bode plot. There's a problem. You can look at this problem, pretty straightforward problem. Basically, we're going to find the transfer function first, which will be this. And then we're going to go ahead and plug in j omega for s right here, and then plot the Bode plot and plot the phase Bode plot and magnitude Bode plot, both of them. Okay, so look at that. If you don't understand it, ask me. And then I have put down some of the exercises as well. 8.1, 8.2, and I think 8.3 I did not draw it, although we have the expression, I think, but I did not draw it. So make sure you do it. I'm going to assign a set of homework as well for practice. So do this in chapter number 8. This is important. Bode plots, basically, that I'm going to ask you. Don't worry about the quadratic equation Bode plot. I'm not discussing it, so I'm not going to give it to you. But whatever is discussed, make sure you go over it, understand it, do some problems that are given in the tutorial, in the text right here that I'm posting, so that you can get practice, and do some of the exercises that are at the end. I have done a couple of them. Do at least a third one. I'm going to be posting the third project from this, where you have to draw the Bode plot, but that project is easy. You don't have to break it down into individual factors. All you have to do is, you have the gj omega, just take the magnitude of that, multiply that by 20 log, and then plot that versus omega. That's all you have to do versus the semi-log scale, right? So I'm going to discuss the project as well, but the project is very straightforward. So if you have any question, then again we'll discuss that, but this is basically what chapter number 8 is.